Hi, in this video we are going to see some examples on simplification of Boolean expressions using Boolean algebra. Boolean algebra is a mathematical system with a set of elements, a set of operators, and a number of unproved postulates. Boolean algebra is used as a tool for the analysis and designing of logic circuit. There are De Morgan's theorems which also considered to be under Boolean algebra, and we are going to see these two De Morgan's theorems. Let us see the first theorem. De Morgan's first theorem is stated as complement of sum equals product of individual complements. Complement of sum, that means NOR operation, and it is equal to product of individual complements. So in the form of gates also we can state De Morgan's theorem as NOR gate is equivalent to bubbled AND gate. This is bubbled AND gate. We can prove De Morgan's first theorem by taking these two values of variables 0 and 1, and hence there are four possible combinations of A and B. So by taking these four possible combinations, we can prove LHS equal to RHS. The De Morgan's second theorem is complement of product. Complement of product equals sum of individual complements. Complement of product is nothing but NAND operation, and hence we can state it in the form of gates like this. NAND gate is equivalent to bubbled OR gate. And in the similar way, we can prove De Morgan's second theorem by taking different possible combinations of A and B. We know in Boolean algebra, the variables can have only two values, 0 and 1, and hence we can take zeros and ones for A and B, and we can prove LHS equal to RHS by putting these values in the LHS expression and in the RHS expression. And hence we can prove De Morgan's second theorem also. Now, Boolean algebra is used to simplify digital circuits. We always desire for the simplest circuit implementation with smallest number of gates and wires. Boolean algebra helps to reduce Boolean expression to its simplest form. In Boolean algebra, variables can have only two possible values, 0 and 1. And the operations on the variables are logical operations. These are not arithmetic operations. These are logical operations. OR operation, AND operation, NOT operation. These are logical operations. Let us see some Boolean laws that we can use for simplification of Boolean expressions. This is commutative law. That means A plus B is equal to B plus A, and A dot B is equal to B dot A. Some of these laws we have studied in normal arithmetic also. Associative law is A plus in bracket B plus C is equal to A plus B in bracket plus C. Similarly for AND operation, A and in bracket B and C is equal to in bracket A and B and C. This AND can be, you can read it as A dot in bracket B dot C or A dot B in bracket dot C. Next is distributive law. A plus BC is equal to A plus B into A plus C. Similarly, A dot B plus C is equal to A dot B plus A dot C. So, A can be distributed with B and C in OR operation as well as in AND operation. Substitution law. If A is equal to B, then in this expression A plus C is equal to B plus C. That means A has replaced uh, B has replaced A here. Similarly, in AND operation also, A dot C will be equal to B dot C then. Some more Boolean laws are laws. A or 0 is equal to A. This plus is OR operation. So you can read it A plus 0, but it is an OR operation. So A plus 0 is equal to A plus 1 is equal to 1, A plus A is equal to A plus A bar is equal to A is equal to 1. We can prove these laws, or we can verify these laws by taking two possible values for A. For example, in the first say law, A plus 0 is equal to A. If when you put possible values of A, for example, A can have 0 value or A can have 1 value. So in this case, if we take, for example, A plus 0 is equal to A. If we take A equal to 0, then 0 plus 0 is equal to 0. So A plus 0 equal to A. A we have taken 0. If we take A equal to 1, then 1 plus 0, and what is 1 plus 0? It is 1. So A plus 0 is equal to A. So we can verify these laws by taking two possible values of variable 0 or 1. Right. So some more OR laws. A plus A is equal to A, and A plus A bar is equal to 1. AND laws. A and 0 is equal to 0. That means A dot 0 is equal to 0. Or this is AND operation, means we can consider this input A or these two inputs given to AND gate. When one input to AND gate is 0, its output is 0. Whatever is the other input, irrespective of other input, AND gate produces 0. So A and 0 is equal to 0. Similarly, A dot 1 is equal to A dot A is equal to A, and A dot A bar is equal to 0. Absorptive laws. A plus AB, A variable is repeated in the next term. A plus AB is equal to A. So that the variable which comes along with A in the next term is absorbed in A. Similarly, it is true for AND operation also. A dot A plus B is equal to A. Next is inversion law. A bar bar is equal to A. That means 2 times inversion is cancelled with each other. So A bar bar is equal to A. There are some other important rules also. These are used for simplification of Boolean expressions, and these are actually simple expressions which can be proved. A plus AB is equal to A. This we have seen, absorptive law, isn't it? And how we can prove it? See here. In these two terms, we can take A common, and then what remains is 1 plus B. And what is 1 plus B? 1 plus B is 1. That means A into 1. And A into 1 is A, which is RHS. Right? Similarly, this other a rule also we can use while simplification of equation. A plus A bar B is equal to A plus B. Now here we can distribute A with these two terms like this. A plus A bar bracket complete into A plus B. A plus A bar is 1. So 1 into a plus b will result into a plus b, right? In the next rule here, you have two brackets, so you can just multiply. So a plus a c plus a b plus b c. A or in all these three terms. Okay, let us take one more step. A is A dot A is A plus AC plus AB plus BC. In these three terms, we can take A common, and hence it becomes A in bracket 1 plus C plus B and plus BC. 1 plus anything, 1 plus C plus B, 1 plus these variables is equal to 1, and hence what remains here is only A, right? A and then plus BC, which is equal to RHS. So in this way we can prove these rules. One more part is there in Boolean algebra, and that is duality theorem. According to duality theorem, the following conversions are possible in given Boolean expression. What are these conversions? We can change each AND operator to these conversions are taken simultaneously. Okay, change each AND operator to OR operator, then change each OR operator to AND operator, and complement any 1 or 0 appearing in the expression. Then the resulting expression, that means the new expression, will also be a true identity. Let us take an example of one identity, say a dot 1 is equal to a. We know this identity. Okay. Now change AND operator to OR operator and change 1 or 0 to its complement. That means a plus this operator will be changed to OR operator. A plus and 1 will be changed to 0. So a plus 0 is equal to a. This is also a true identity, right? So duality theorem helps us in finding new identities if we know one identity. Uh, Let us take another example. Say a dot 0 is equal to 0. If we change this operator to plus and 0 to its complement, then a plus 1, again 0 will be converted to its complement, that means 1, and a plus 1 is equal to 1. This is also a true identity, right? So this is what is duality theorem. Now let us see some examples on simplification of Boolean equations. The first one, prove the following using Boolean laws. Here you have given some expression on left hand side and you have to prove it in the simplified form as A into B plus C only, right? So let us start with LHS and let us simplify this expression. So we can consider, see, if we consider this first term and the third term in the expression, we can take AB common. So taking AB common, what remains is C plus C bar. And the second term will be as it is plus A B bar C. So we know C plus C bar is 1 and hence AB plus AB bar C. Now in these two terms we can take A common and what remains in the bracket is B plus B bar C. We know A plus A bar B is equal to A plus B. or b plus b bar c is b plus c. So this bracket can be represented as b plus c, which is equal to RHS, right? What Boolean laws we have used? Here we have used c plus c bar is equal to 1. Here we have used b plus b bar c is equal to b plus c, right? So we should know the results also. Let us see another example. Here prove the following again using Boolean laws. Starting with LHS, the expression is A XOR B bar. Let us expand A XOR B. What is A XOR B? It is A bar B plus A B bar XOR operation bar. Now using De Morgan's theorem, complement of sum equals product of complements. Complement of sum equals product of complements. So individual complements. So complement of this term, that means A bar B bar, complement, individual complements, and complement of this is A B bar bar and product, that means dot. Complement of sum equals product of individual complements. Again using De Morgan's theorem, complement of product equals sum of complements will give you A plus B bar dot A bar plus B. Now you can merge these two brackets by multiplying as A bar plus AB plus A bar B bar plus B B bar. Now we know A dot A bar is equal to 0. That means this term will get cancelled. B dot B bar is also 0. This term will also get cancelled. And what remains is AB plus A bar B bar, which is equal to RHS. Hence proved. Let us move further. One more example. Again here also you have given some expression on LHS and we have to prove it equal to this as well as this. So let us start from LHS. Here we can consider these two terms together and these two terms again together. Here we can take AB bar common and here we can take AB common. So A bar BC plus AB bar common, C bar plus C. What remains in bracket is C bar plus C. Again in next two terms AB common, C plus C bar. And now we know that C plus C bar is equal to 1. So this will become A bar B C plus A B bar plus A B. Here in these two terms we can take A common and hence it will be A bar B C plus A into B bar plus B. Again B bar plus B is equal to 1. So it will be equal to A bar B C plus A. Now here we can use this Boolean law that A plus A bar B is equal to A plus B, absorptive law. So instead of B, there is BC, and hence A plus A bar BC can be written as A plus BC, which is equal to RHS, this part, isn't it? A plus BC. And here, next step is very simple. This A can be distributed with BC, and hence it will be A plus B into A plus C, which is one more part of RHS, A plus B into A plus C, right? Hence, proved. Distributive law. Let us see next example. Again, one more expression is given, and we have to simplify it to just Z bar. That means a logic circuit which will need many inverters, then many AND gates, and then OR gates. That circuit can be just minimized to a single NOT gate which is receiving Z input only. Okay, so this is the power of Boolean algebra, which helps us in simplifying big logic circuits into simple circuits. Right, so let us see how this can be simplified. Starting from LHS, here in every term there is Z bar. So let us take Z bar common, and then in bracket we'll have Y bar plus W bar X bar plus W bar X Y plus WY. Now again Z bar common, and here Y bar plus W bar X bar, keeping it as it is, plus here we can have take Y common in these two terms. So what remains is, let us have this as a square bracket, and then Y common. What remains is W bar plus W bar X plus W, square bracket complete. So in this term, W bar X plus W, we can write it as W plus X, right? So Z bar in square bracket, Y bar plus W bar X bar plus Y in bracket, W plus X only, square bracket complete. Next, Z bar in square bracket, Y bar, De Morgan's theorem here. Instead of W bar X bar, we can write W plus X bar, De Morgan's theorem. Complement of sum equals product of complements, right? And plus Y into W plus X. Now here these are complements of terms y and w plus x, right? So reverse De Morgan's law will give you y into w plus x bar, complement of product equals sum of complements, right? So reverse De Morgan's law we have used here, and plus the next term is y into w plus x. Now if you observe these two terms, this if you consider say a, this will be a bar, and hence a plus a bar is equal to 1. So this bracket, square bracket, is actually equal to 1, and hence what remains is only z bar, which is equal to RHS. Okay, so we can write the reasons also here, that we have taken y common here, then we have used De Morgan's theorems in these two steps here, and we have proved the big expression on left hand side equal to just a single term on right hand side. Let us move towards the next example. Here we are given one Boolean expression and we have to simplify it. RHS is not given, but we have to simplify it to its simplest form using Boolean laws. So let us observe the given expression and let us see how we can take terms common. So if you observe this, first term and last term, b bar c can be common and a bar plus a will remain. So in first and last term, we'll take b bar c common. And in these two terms, we can have b c bar common. In the two middle terms, we can have b c bar common. Okay, so let us take b bar, c bar common in first and last term, and what remains is a bar plus a. Next, in second and third term, we can take b, c bar common and remain in the bracket is a bar plus a. We know a bar plus a is equal to 1, so b bar c bar plus b c bar. Again, in these two terms, we can take c bar common and hence in bracket b bar plus b. Again, b bar plus b is equal to 1. B bar plus b is equal to 1. So, what remains is only c bar, right? So, we have again simplified this equation into a single term c bar. If you draw a logic diagram for this expression, you will need many NOT gates, then you will need these AND gates, then you will need OR gate. But all these gates are replaced with a single NOT gate which is receiving C input, right? So this will be a single circuit which is this will be a single gate which is receiving C and producing C bar. So this big circuit can be simplified or minimized into a single gate. So in this way we have seen some examples how to simplify Boolean expressions using Boolean laws. Thank you.